Okay, so we are going to be talking about concentration. And so this is something that I kind of talked about last class period. Like this is the stuff that I literally would do all the time in lab. So there are a lot of applications of this and uses. I mean, it's talked about in so many research articles of different concentrations of trace elements and toxins that you guys see. The EPA sets all these like requirements that you making sure that our bodies of water don't get polluted. So concentration is a big deal when we talk about chemistry. And so just a general summary of the definition is just, it's a measure of some amount per unit of volume. And so as you can assume, we know we have lots of different units of amounts. We talked about moles, we talked about grams, we can do things like change our volume, or maybe we are just looking at a percent by mass. So there's lots of different ways we can say state a concentration of something. We're going to talk about them. So the first thing is what you guys learned how to do yesterday, figuring out from table G. We had all of those lines, we called them solubility curves. And so these were just in units of grams of solute per grams, or per 100 grams, sorry, 100 grams of H2O. So we talked about these units already. That was the y-axis. Then we introduced molarity during rate laws. Does anyone remember what the units were here? Moles per liter, exactly. But we're going to go a little bit farther and say this is our moles of solute per liter solvent. And so molarity is by far the most commonly used concentration in labs. And so we're going to talk about figuring out the molarity of a solution. And so one, making sure that your volume is units of liters. We're going to determine how many moles. So we're going to kind of go back to some of that stoichiometry and conversions here. So we have to figure out moles of solute, and then we just divide moles by liter to find the molarity. So this first example here already gives you things in the units that you need. It tells us moles, it tells us liters. And so we're just setting up our 2.0 moles over 4.0 liters. That gives us 0.50. Now, you can write unit as M, or I don't care if you guys want to write it as moles per liter as well. They're the same thing here. One thing I will tell you guys, I know that I'm not usually picky on sig figs. I will be picky here. When you are making concentrations of solution, you can't say things that are more exact than they actually are. So the biggest thing here is making sure that our final answer has the same amount of sig figs of the one with the least amount of sig figs, because we're dividing. That's the rule. So you don't have to worry about counting decimal places. You'll just look, okay, 2.0 and 4.0. They both have 2 sig figs, so my answer better have 2 sig figs, okay? All right, the next one here says, what's the molarity of a solution if it contains 2 moles of sodium chloride and 250 mils? Now, we have our moles, but what's wrong with our volume? It's in milliliters. So the common conversions between milliliters and liter, like I expect you guys to know this. I will not require you to show me the conversion on paper because it's rather simple, but I'll show it for this sake just to remind you guys how to do it. So 250 milliliters, there are 1,000 milliliters for every 1 liter. That gives us 0.250 liters. So you can just move the decimal 3 places to the left. If you're in mils, I'm okay with that. But just remind you guys why we can do this is because of those conversions here. Now, all that's left, putting our moles over our liters. Our 2.0 moles limits us on sig figs. We can only have 2 sig figs here. So 8.0 molar. And so, yeah, so when we refer to a concentration, we call it molar. So you can think of it like the tooth. So I have an 8 molar solution. That's just giving you guys some of the terminology there. All right, now this last one is given to us in grams. Does anyone remember how to go from grams to moles? Yeah, the molar mass. So one thing, we're gonna have to refresh ourselves on a couple things here. One, how to find molar mass and the proper way to round it, and then how to use it to go from grams to moles. So I write molar mass as just capital MM. And so we need to find the molar mass of NaOH. And so looking at the red numbers on your periodic table, those are, we can count up their atomic masses and turn it into molar masses. We multiply the molar mass of one atom by how many we have. In sodium hydroxide, we have one of each, so we don't have to worry about multiples. So we are taking the mass of one sodium, which is 23.0. One oxygen, we are adding 16.0. And we're adding that to one hydrogen, 1.0. Now, notice how I rounded all of these off at the 10th place. That is what's expected. So when you guys are doing these things, I expect to see 10th place, even though notice how all three of these round 2.0. I still expect you to show that. That makes our molar mass 40.0 grams per 1 mole. So we have to remember that the definition of molar mass is how much a mole of something weighs. Well, in our case, we want to find our moles. And so we're going to start with our number of grams given to us. So if we have 20 grams of NaOH, we're going to set up our conversion factor using our molar mass. So there's a couple of ways you can think about this. We want grams to cancel. And so if we remember this over our imaginary one, technically that's on the top of a numerator. So we're going to want to put our 40 grams of NaOH on the bottom, because this allows grams of NaOH here to cancel with the one here. And our molar mass always goes with the unit 1 mole, because again, that's the definition of molar mass, the mass of 1 mole. Well, 20 divided by 40 gives us 0.50 moles. We now have our top number, so we'll take 0.50 moles, divide that by our 2 liters, which gives us 0.25 molar. Any questions on this here? So I know it's been a while since we've done conversions, but the biggest thing is if you have grams, you divide by the molar mass. If you have moles, you multiply by it. So we'll do some examples here. Any questions before I move on? Okay. All right. The next, which I think is probably one of the more important ones, is this is pretty much what I would do, is saying, if I want to make this concentration, how much do I have to add? So we determine what molarity of concentration we want. Then I have to figure out how much I want to make, how many liters of it. And then I'm going to figure out the number of moles. So to solve for moles here, you will have, I think I left the space to put in here. If you have, think about molarity being equal to moles over liters. If you were to just solve for moles, it would just end up being molarity times your volume in liters is equal to the number of moles. So you're just multiplying your liters by your molarity to get your moles of your substance. And then you'll use a conversion using molar mass to solve for grams. So we'll do an example here. This asks how many grams of sodium hydroxide are needed to make 4 liters of a 0.5 molar solution. Well, the first thing I'm going to do is figure out how many moles of NaOH I need. And that is going to be equal to my molarity of 0.50. And now I'm going to write my molarity in terms of moles over liter to show you guys why this works. Because if we have moles over liter multiplied by our volume wanted, our units of liters cancel out, giving us the unit of mole. If you multiply that, you get 2 moles of sodium hydroxide. And then the last thing we do is have to do a conversion. So for every 2 moles of sodium hydroxide, we're going to use the molar mass again. We already figured out it was 40 grams per mole. But now we're going to put the 40 grams on top because we want the 1 mole to cancel. And another way you could think about it for these conversions is the target goes on top. The target number is grams. We put that on the top of our fraction. So that's another thing I use to remind myself. If you solve that, you'll get 80 grams of sodium hydroxide. Any questions about figuring out how many grams we need? So if this is me figuring out how much to make this, I would go to the balance, weigh out 80 grams of sodium hydroxide, and I would put that into a volumetric flask that I can fill up to 4 liters and mix it up. So this is actually how you would make a solution. All right, this next one here, this gives us milliliters. So we have to first convert our mils to liters before we can do this, because if you look here, if we used mils, it wouldn't cancel out units. We have to make sure our units of volume are the same. And so we're gonna have to first convert mils to liters. So like I said, you could set it up nicely, or we could just move the decimal 3 points to the left and show that we have 0.500 liters. And we're gonna multiply that by our concentration of 0.100 moles per liter. That gives us our moles of KCl, which end up being 0.0500 moles of KCl. We then can take our 0.0500 moles of KCl. We're gonna get ready to multiply it by its molar mass. If you use periodic table, potassium plus chloride equals 74.6 grams of KCl for every 1 mole. That means it would take 3.73 grams of potassium chloride. Any questions here? Yeah, go ahead. So that 1 mole, so you don't, sig figs in conversion factors do not affect sig figs of your answer. Good question though. Any other questions? Okay, next page. Now we're gonna switch gears from molarity to parts per million. And so when you first are introduced to this unit of part per million, it can kind of be weird. But I'm gonna first define it. This is defined as your grams of solutes over your grams of solution. We then take that and multiply that by 1 million. To save you guys time writing for these problems and in your calculator, don't forget 10 to the 6 is the same thing as million. So you can just multiply by that as well. And so why this is important is when we are determining trace amounts of things. So again, I talk about the EPA setting trace amounts to, like, for example, lead from batteries that just people end up throwing away and not actually recycling can get into our water systems. And so they set an amount, but the quantity per wire is very little. So when I do this first problem, I'll explain why it helps to multiply it by million, just to have a unit that the value makes more sense. It's kind of like, you know why we use scientific notation for really small decimal? This is like the equivalent of scientific notation in units of chemistry, in the sense where it gets rid of that really big decimal. Okay, so what is the concentration in parts per million of lead ions in 100 grams of tap water with 0.000450 grams of lead ions dissolved in it? So all we have to do is take that grams of our solutes. We are determining that is lead because that's what's dissolved. So we take 0.000450 grams of lead. We are going to put that over our grams of solution, which is water, and it said we have 100 grams of it. We will multiply that by a million, or 10 to the 6th power, and you would get 0.450 parts per million. Now, if you think about the reason why we do this instead of use it, you might be thinking, why don't we just use molarity? Well, in this case, if you try to convert the top thing grams to moles, it would get even smaller because you'd have to divide by the molar mass. The decimal on the top would get even smaller. And there's 100 mils in 100 grams of water. So you're just making the decimal even bigger. So again, we do this multiplied by a million. We give it parts per million. So people know when we're talking about really low concentrations, we have a way to talk about it. All right, next one here. When a well is tested, it's found that a 1 kilogram sample of water contains 0.00330 grams of cadmium. What's the concentration in ppm? Well, I think you guys, your paper has 3 zeros after the 1, right? Not 2. I fixed that. Okay. So we have 1 kilogram. So the conversion to get to grams, because that's what is necessary for ppm, is that for every 1 kilogram, because kilogram is the bigger unit, there are 1,000 grams. So this would give us 1,000 grams then. And so like going from mils to liters, you go 3 decimal places to the left. For this, you go 3 decimal places to the right. So again, I'm showing you the conversions, but I'm okay with you just moving decimals. Then to set this up, we just take our 0.00330 grams of cadmium over 1,000 grams of water. Multiply that by 10 to the 6, and we get that there is a concentration of 3.30 parts per million cadmium. Yeah.
Why is it 10 to 6 instead of 10 to 5?
I totally get it. Don't worry, I made sure to Google it before I just put it in because I'm like, I think this, but I don't want to get this out.
10 to the first is 10. Yeah.
What is 10 to the first?
Yeah.
It's just
10.
And that has
And then
one
10 to
zero.
the second.
10 squared is 100.
However many zeros there are, that's the. How many zeros there are. It's how many zeros there are. It's saying there are 6 zeros. It messes me up too. Just think about the zeros. That's what I do. The decimal makes no sense. Just think about the zeros. Okay. However many zeros there are, that's what the exponent is. Yeah.
Hi, this is my honors class. Nope, that's okay. All right, so if we have a 50-gram sample of solution that's evaporated until it was dry, the concentration of solute, if the concentration of solute was 25 ppm, what was the mass that should be left over? So this is where we just have to solve for a different part of the equation. So if we think of our parts per million being equal to our grams of solute over grams of solvent times 10 to the 6. What it's asking is, what is the mass of solute left over? That means we are solving for this top number here. Solving for the top number means we want to divide by 10 to the 6. So that would go over to the denominator over here. We would want to multiply by grams of solvent, move to the numerator on the other side. That gives us the equation. Grams of solute is equal to ppm times grams of solvent divided by 10 to the 6. So plugging in our numbers, we get 25.0 multiplied by 50. Divide that by 10 to the 6. That must have meant that there was 0.00125 grams of solute dissolved. Any questions about this one? These last couple things, piece of cake. No issue. You guys should have no problem with these. These are percent by mass. So instead of doing crazy stuff with ppm, we're just multiplying the percentage by 100. So it's going to be grams of solutes over grams of solvent still times 100. So reading this problem here, it's just saying we have a 25-gram sample of a sodium chloride solution. We evaporate it, it has 2 grams of sodium chloride. What's the percent by mass of sodium chloride in the solution? That is as simple as 2 grams over 25 grams times 100. This gives us 8%. So this is 8% sodium chloride by mass. Yeah. All right, one last thing to get through, guys. It's just for volume then it's mils of solute over mils of solution. So I know we use liters for molarity, but for percent by volume, for whatever reason, we're gonna use milliliters. So for this example, we would just take our 33.2 mils of ethanol and put that over 50 mils of sample. Multiply that by 100, we would get 66.4% ethanol by volume.